Okay, Bismillah. Assalamualaikum and good morning, everybody. So this is our second last class. So today we're going to cover two topics. It's about pavement stresses and structural design of flexible pavement. So I have mentioned to you last week that these two last final classes this week and the one that we're going to have tomorrow is can be considered as important classes. You might want to pay attention to these two classes. On top of the other classes, of course, but in terms of pavement and asphalt design and also theory, these two classes is very important. So before this, we have discussed last week lah. We have discussed optimum binder content of asphalt mixes. So we have covered that, we have learned that different type of pavement would require different amount of optimum binder content. So the factors that influence the optimum binder content is aggregate type and type of mixes, and on top of it all, the optimum binder content will be influenced by the type of bitumen that you use. Okay, the type of bitumen. The less viscous the bitumen is, the less amount of bitumen, that optimum binder content you are going to get. The higher the viscosity of a bitumen, the higher optimum binder content that you will need to use. This is because the film thickness, when the bitumen covers the surface of the aggregate, thicker bitumen or more viscous bitumen will have a thicker layer. Okay, will have a thicker layer, and that will increase the amount of bitumen that you need. Aggregate content, for example, if you change the type of aggregate, or you add in palm oil kernel, something like that, that will increase the absorption of bitumen, and thus that will increase the amount of optimum binder content that is needed. Porous asphalt compared to dense asphalt will require a higher amount of bitumen because the grading of the mix is smaller, and the surface area in that mix, surface area of the aggregate in that mix is higher. Therefore, it would require a higher optimum binder content. Okay. Okay, just back a little bit about the asphalt just now, about the bitumen. If you are using polymer modified bitumen, the viscosity of the bitumen is going to be higher, and that also will increase the percentage of optimum binder content. Okay, so from there, we'll need to estimate what we will cover today, which is pavement stresses and deflection, and then we'll cover on the structural design and thickness. So the origin of the stresses and deflection calculation was introduced by Business, and in his analysis, he is using a point load, a concentrated point load on the pavement surface, and another variable that is being used is the depth to the point of interest that we want to calculate the stress and also the deflection. So Business introduced this formula to estimate the value of stress using the wheel load, okay, and also the depth. And he used the variable K, which actually explains the depth and the radius of the point of interest. Okay, this estimation can be a little bit inaccurate because the loading is a point load. So instead of a point load, the loading that is transferred by the vehicle's tires to the pavement is actually a circular or maybe an ellipse. So we assume at this time, we're assuming that the contact area is circular. So the area for the loading to be transferred to the pavement can be estimated using this formula here, which is a function of tire load and also tire pressure. Tire load meaning that the loading that is being sustained by the vehicle, okay, transferred to the tire, and tire pressure meaning that the pressure of the air that you pump into the tire. The lower the pressure, the higher the contact area is. Okay, so the contact area is a function of loading and also tire pressure. Okay, so Alvin and Illyrie have provided the solutions to further estimate the stresses, strains, and deflection. So they have proposed three equations. The first one is to estimate the vertical stress, here, sigma z, and then radial horizontal stress, sigma r, and the deflection value, delta z. So all this is a function of tire pressure, and has the other variables are variables A, B, C. There is no D, E, F, and H. Okay, let's look at it one by one. So sigma z is the vertical stress in kPa. Mu is the Poisson ratio of the mix. Okay. Delta R is the radial horizontal stress in kPa. And P here is the pressure to the loading due to the small p here. Is the pressure due to the loading in kilopascal. E is the modulus of elasticity of the mix in kPa. So this is why we create last week Marshall cakes, Marshall samples that I have explained to you before we use it as a pavement. So we create those samples and we test it in the lab to estimate the value of modulus of elasticity. Okay. The variables of A, B, C, F, and H are presented in table 1 here. So it depends on Z, the value of Z, R, and A. Z is the depth of the point in question. So you have a tire stopping on the pavement. So Z is the depth underneath the pavement that you want to estimate the stress and also the deflection. R is the radial distance from the center line of the point load to the point in question. For example, so this is the point load. Z is the distance, z-axis z-axis underneath the loading. And R is the distance radial, meaning that it goes somewhere here. So it goes down, but it's going to either towards the x-axis and the y-axis, the radius. So the distance between the loading and the point is R. Radial distance, radial distance. So A is the equivalent load radius of the tire footprint. So this is what I've showed here. Value of A. All right. So to estimate the value of function A, function B, function C, function E, and function F, you need to use table 1 here. So here, this is to use to find the function A. So you need the ratio between radial distance and A, and the ratio between the depth and the tire footprint lah, A. So using this value, you can estimate the value here inside this table. So this is for function A. You have function B, function C, function E, and this function F, and this one is function H. Okay. So let's look at an example. A tire have a pressure of 690 kPa, contact radius 125 millimeters, modulus of elasticity 345,000 kPa, and the Poisson ratio of that mix is 0.45. So this question requires us to calculate two things. The first thing is calculate the radial horizontal stress and deflection point on the pavement surface directly under the center of the tire load. Okay, what it means that it does not have R value. It only has Z value. R is 0. Secondly, it asks us to calculate the radial horizontal stress and deflection at a point at a depth of 500 millimeters and radial distance of 250 millimeters. So it is, the depth is 500, radial distance is 250 millimeter. So it's like eccentric loading lah. Eccentric loading if you are studying column, isn't it? Okay, if the loading is a little bit off center, then that is the radial distance. Okay. Solution. So you have 690. So these are the question. This is the question lah. So in the first part here, the radial. Oh, dia tak ada depth eh. Okay, directly under the loading, Z is 0, and the radial is also 0 in this case. So now the ratio Z over A is 0 over 125, where here 125 is the circular contact radius. And here radius is also 0, and the A is 125. So Z over A is 0, R over A is 0. So from the table 1 actually, in this question here is table 4.1. You estimate the value of A, B, C, F, and H. So 0, 0. Value of H, 0, 0 is 2. Value of F, 0, 0 is 0.5. So you can see H is 2, F is 0.5. So you convince with you proceed with other values as well. So now you just use this formula where P here, small p is the tire pressure, A is the value from the functions, mu is the Poisson ratio. So you calculate the radial horizontal stress, delta R, and you get 655 kPa. And then you calculate the deflection using the same formula proposed by Alvin and Ullery. So you can get here, so this is the modulus of elasticity, this is the tire pressure, Poisson ratio, small a is the tire footprint, and the other values of function A to H. So you get the delta Z, the deflection is 0.399. Okay, the second part of the question, it asks us to estimate the point of interest now is 500 millimeters below the pavement, below the tire lah. And the radial distance is 250 millimeters away from the center of the pavement. So now you calculate the value ratio between Z and A, 500, the depth, and A tire footprint. The radius here is 250, tire footprint 125. So Z over A is 4, and R over A is 2. Again, go back to the tables. Z over A is 4. Somewhere. Mana? Sini R over A is 2. 0.22188. Value of H. Okay, this one. Okay, you estimate for every function values, and you calculate the radial horizontal stress. So for this depth, at this depth, you get the stress is at 7.64 kPa, and the deflection is 0.076. So you can see here the amount of stress, 500 millimeters, half a meter, underneath the pavement is significantly less, 7.64 kPa, compared to directly under the tire, the stress is 655 kPa. Okay, and the deflection on the surface of the road is 0.4, okay, or 0.399 millimeters, and deep underneath the pavement, the deflection is 0.076 millimeters. That's why the thicker the layering are, the better it is to sustain the better it is for the subgrade lah. If you have a weak subgrade, but if the subgrade is too weak, okay, you cannot basically use the subgrade. You need to remove it or do some kind of treatment before you can actually design the pavement on top of it. On the other hand, it also, if you keep on adding the thickness of the layers, the cost of the road is going to be very expensive. So you have to balance between soil stability, improvement of the subgrade, and also the thickness of the pavement layer. Okay. So this is the first part. The second part is the design, the structural design of flexible pavement. So the objective here is to put it short, is to decide what are the thickness for the layers that you want to use for the road base, for the binder base, for the wearing course, or the sub base. Okay, material for this layering basically have been decided lah. Okay, but you need to determine the thickness. So the principle of design that we assume that the composition, density, and thickness of the entire layering paving materials here, whether it is bituminous, stabilized granular materials, unbound granular materials for road base and sub base, shall be so that they perform as an integral structure and meet the intended performance requirements. Okay, so again, this is a bit of a refresher of last week's content. Okay, this actually came from Arahan Teknik Jalan this one lah. I think you can download it online, but the one that I got here is already being copied from this manual. So subgrade is a soil or rock formation that forms on the foundation of the structure, pavement structure. So the pavement shall be designed so that stresses and strains remain within tolerable limits. These limits are a function of elastic stiffness and bearing capacity of the subgrade and of the traffic volume is designed for. Okay, so when required and specified, weak subgrade material shall be replaced with selected materials or stabilized up to depth at least 300 millimeter below subgrade. The most common soil improvement method is to have loading. I forgot the name of the simple one. Meaning that they bring in earth, soil from other locations, and they just fill in the area, the point of interest. Okay, this will react as extra loading that will compact the subgrade underneath. This will take a long time lah, because of the need the time for the soil that you actually put in on top of the subgrade to settle down, and then you remove that soil, and then you compact the earth, further compact the earth. That's one very common and very cheap, but it takes a long time. Okay, so if you have a very terrible quality of materials, then you need to remove at least 300 millimeters of the original material and replace with a better quality material and compact it properly. Okay, the most important thing is compaction. So if you look at the specification, normally the compaction is being done every 300 millimeters. 300 millimeters ke 6 inches eh? You dah practical ingat tak? Saya tak silap saya 300 millimeters lah 1 feet. Saya dah lupa 6 inches ataupun. So the earthwork compacting this new soil must be done in layers, small layers. If you compact everything, you put in everything 2 feet high, and then you compact it, the strength is definitely not going to be there. Okay, so if you ask me, actually the most important part is the subgrade lah. Okay, this subgrade, because that's why your techniques, in my opinion, is a very good field, because in civil engineering, everything has been constructed will require your techniques. Whether you are you are constructing a highway, whether you're constructing a building, everybody is constructing on earth. Nobody is designing something hanging on the air. So geotechnics has a lot of projects, in my opinion. Okay. Okay. And then you have the subbase, which consists of a layer of specified material considered as lower road base that supports the upper road base. Because the stress are lower in the subbase, subbase material are usually of lower quality and stiffness, but it is not as low as this is road base, bukan subbase. The quality for road base is not as low as the subbase lah. So it can contain bituminous mixtures. Okay. Where the bitumen, the amount of bitumen that you mix for this layer is lower, much lower compared to the wearing course, but it is being bound. So, or you can stabilize the layer with cement using emulsions, okay, and mechanically stabilize, meaning that compacted lah. Or you can use unbound crush aggregate if the quality of the subgrade is good. Okay, so you can see that if normally if it is you are designing the pavement for a heavily traffic road, this road base is definitely going to be bound. Bound meaning that the aggregates you will have asphalt content in it or cement. Okay. And this is the binder cost that is right below the wearing cost. It can also be that you don't have this binder cost, but you can have directly a thicker wearing cost. Or you can have same type of pavement for binder cost and also the wearing cost. So this is considered as the part of surface layer of the pavement. Okay, so it should have good resistance to shear into distress because the shear is highest at depth of 0.9 times the radius of contact, the wheel radius wheel contact area. So 0.9 times of the radius. That is the depth where the shear stress highest under the pavement. So with that, the depth corresponds to, for most commercial vehicles, at a depth of 8 to 12 centimeters below the pavement surface. Okay. Bituminous wearing cost, the topmost layer, shall meet both structural and functional performance and have adequate durability, has extra friction characteristics and smoothness as well to give you comfort. You need to have friction, but not too high where it sacrifices the smoothness and the right quality. So this is, so the other important characteristic of this layer is that it must be waterproof lah, if it is not porous pavement, of course. So we have three samples here of typical flexible pavement structures used by the JKR. The first one here is the single carriageway low volume road. So you can see here the topmost layer, the wearing course is actually just chip seal. Okay, underneath the chip seal is aggregate, crush aggregate. And then you have a subbase and a drainage layer. Chip seal is not a structural, does not have a structural strength actually. So the strength will lie in the friction and the strength of the underlying layer. The purpose of the chip seal is to provide friction and provide waterproofing properties lah, so that rainwater does not penetrate under the pavement. Okay. So in chip seal, you just spray a layer of bitumen and then spray a layer of aggregate, compact it, and then spray another layer of bitumen. That's it. Okay. In Australia, if you have very good quality of subgrade, it is possible to lay chip seal directly on top of the subgrade. So in most cases actually, but you need the road base and sub base lah. But if the property of the subgrade is very good, you just need to compact the subgrade, treat it maybe, and then can have the layer of chip seal on top of it. But this is not for heavily used lah. Okay, this is just for low volume roads. The second part here, you have the single carriageway major road, where you can see the usage of ACWC here as asphaltic concrete wearing course and asphaltic concrete binder course. And then you have the binder road base and sub base as usual. And the last one here is the same thing, but this is for dual carriageway road. More or less the same. So in section 2 here, information needed for pavement design. First, you need the types and volumes of commercial vehicles. Okay, you can have a traffic count, but the most important input is actually the percentage of commercial vehicle. Okay, because they are the ones that will contribute to the highest deflection and stresses that need to be supported by the pavement. Okay, and then you need to know the design life. Normally it's 20 years lah. 20 years for the design, for the lifespan, and then subgrade type and strength. Okay, definitely you need the CBR value or falling weight deflectometer readings. Okay, these two types of tests they normally conduct to get the value of the strength of the pavement, strength of the subgrade. Types and properties of paving material use, this is very common lah. And also the environment to which the pavement structure will be exposed. All right, so this is the generalized design procedure. So you need the design input, traffic volume, axle loading, traffic speed. As I mentioned last week, faster vehicles will induce lower stress to the pavement. So if the performance of our pavement is our only concern, we should increase the speed limit of our highway so that the loading will be less. That's just a joke, right? Okay, and then you need the strength of the subgrade, strength of the paving materials, temperature and water and also drainage conditions. So all these inputs will be used to model the type of pavement and the thickness of the pavement that you need. So that will also be used to calculate the stress, strains, so on and so forth. The two types of strains on the pavement performance is the vertical and horizontal strain. Vertical strain occurs on top of the subgrade, and horizontal strain at the bottom lowest at the lowest bound pavement cost. Lowest bound maknanya kalau if the uh, road base is bound, then it is under the road base lah. If the road base is granular, the bound part is only the surface cost, then the horizontal strain, the apa tu? The horizontal strain is under the surface cost. Type and cost thickness of paving materials are selected to ensure that the above strains are within the range, and vertical subgrade strain is adopted as a design criteria to control accumulation of permanent deformation of the subgrade. Okay, the subgrade deformation is a primary function, so this is our main interest lah, the subgrade deformation. As I say that the most important part is the subgrade quality. If the deformation of the subgrade is very low, then the possibility of the layers on top of it to suffer is much less. Horizontal strain at the bottom bound layer is used to control fatigue damage due to repeated load traffic loads. Fatigue meaning that the failures that is being that occurs from repeated traffic loads, meaning that it is a function of it will occur for roads that is very old, that is reaching the design life. Okay, because it has been subjected to repeated numbers of vehicles passing through the pavement all day and night. Okay, and one day it cracks. Okay, so that cracks will develop, and then water can penetrate into the pavement and subsequently will crack the pavement, create potholes and deformations. So the stresses and the failures of pavement, the type of stresses and failures will be discussed in our class tomorrow. So this is the diagram that shows you the horizontal and vertical strain on the pavement. So the horizontal here part is occurring below the bound layer, and the vertical is the stress that is subject to reacting on the top of the subgrade. Okay. So determination of design traffic. Two elements of traffic load that we need to consider is the standard axle or wheel load. We need to know how many axles that is actually passing over our pavement, and then the traffic spectrum and also volume that is actually reacting on the pavement. So you need to convert those traffic into standard axle load, equivalent standard axle load. How many ISALs is going to react on our pavement? One ISAL, as you may recall from last week's lecture, one ISAL is 80 kilonewton. Sekejap, saya silent sikit my phone. Okay, one ISAL is 80 kilonewton. Okay, same with the value that is being adopted by H2O design last week. Okay, traffic data, number of commercial vehicles during year 1 of design period. In the first year, after the road has been completed, what is the number of commercial vehicles that is expected to use the road? And then vehicle class and axle load distribution. what types of vehicles and what kind of loading that we are talking about. Directional and lane distribution factors. Okay. Normally we just divide it into two lah. You have the total annual daily traffic, and then you just divide by two. You assume that the traffic is equally distributed between one lane and the other. And then traffic growth factor. So this depends on the how long is the design lifespan that you want for your pavement. Okay, two types of data for structural pavement design: traffic volume and percent of commercial vehicles from the JKR National Traffic Database. So I suppose that you are very familiar with this data, especially for those who have taken elective subject, highway design and road safety audit. Yeah? So you can see that the traffic volume and the percent of commercial vehicles in the publication published by JKR every few years. And then you must have the actual load studies. What sort of loading does these vehicles use? So these are the actual configuration and the load equivalent factors that you are going to use. Okay, you have different classes here, from cars to motorcycles and also commercial vehicles. So this is the load equivalent factor. It's like PCU, but this one is for loading. So the baseline here is car and taxi, where the load equivalent factor is 0. And motorcycle also is 0, because it is assumed that the loading from these two class of vehicles are insignificant, very small. And then small lorries, you can see the LEF here is 0.1, and articulated lorries, the load equivalent factors is the highest at 4.4. 4.4 lah. This is a factor. Okay, and then large lorries and also commercial vehicle traffic, if it is mixed. If you have a mixed commercial traffic, it does not state whether it is small lorries or is it large lorries, how many articulated vehicles, how many buses, then the CV is 3.7. If you have the separation for the values here, the types of class, different type of class, then you can use different LEF for each class. All right, so in that arahan technique, so they have several steps. The first one is from the traffic count. You get the ADT. Minimum count is 3 days, 24 hours per day. If you don't have a 24 hours count, the traffic volume that you get must be multiplied by 1.2. Okay. If it is the count is for 24 hours, then it's okay. You can directly use the volume. If the volume provided to you only between 6 a.m. to 10 p.m. here, you need to multiply the volume by 1.2. Very important to remember this. All right, and then you need to know the percentage of commercial vehicles as shown in table 2.1 before this, and also the annual traffic growth factor for the commercial vehicle. So usually for the growth factor here, we'll use this table. Tak apalah, tengok ni. So annual traffic growth rate and the design period. So this is the growth factor that we use. And then you need to know the number of lanes and terrain conditions, whether it is flat, rolling, or mountainous. Again, because these three types will have different loading impact, because due to the stresses from the tires of commercial vehicles. Select design period. 10 years are recommended for low volume roads. For normal road lah, minimum design is 20 years. For roads that have medium to high volume traffic. So this is the first equation. You need to estimate the equivalent single axle load for year 1. In this equation, you are only using PCV here, which is the percentage of commercial vehicles that has the unladen weight of 1.5 ton. Unladen weight, berat tanpa muatan. Okay, if berat tanpa muatan is more than 1.5 ton, then it is considered as it counts lah into this percentage. Okay, unladen weight, meaning that the weight of the vehicles without loading. And then the ADT, average daily traffic, and the lane distribution factor from table 2.2 and terrain factor from table 2.3. Table 2.2 here, this is the lane distribution factor. Number of lanes in one direction, 1, 2, or 3 or more. So this is the L value. And this is the terrain factor. Okay, flat, rolling, and mountainous. The second formula, so this is for ISAL year 1, PCV over here. This is 3.7. This is just a factor lah. Okay, for the second equation here, you actually have the the percentage of different type of vehicles. You have the ADT for vehicle class 1. So you have the ADT for vehicle class 2, ADT for vehicle class N lah, whatever class that you have. And for each vehicle class, you'll need to multiply the ADT to the load equivalent factor 1, 2, and N. So if you have a okay, how many small lorries that you have? Let's say 500. So that 500 multiplied with 0.1. Articulated lorries, you have 100. So 100 multiplied with 4.4. So this is this part of the equation. So you add up, okay, all these values between the ADT and the load equivalent factor, multiply with 365 days per year. This is the L, lane distribution factor, and the terrain factor. So this is the other method to obtain the ISAL for year 1. Okay. When you have calculated the ISAL for year 1, you use that value to estimate the design ISAL. Okay, the design single axle load, equivalent single axle load. So in this formula, you will need the R, which is the growth factor, and the value of N, which is the number of the design years. Okay. Or you can calculate the ISAL using TGF here. Okay, total growth factor refer from table 2.4. So it depends on the question lah. If it gives you the value of R and N, then you can use this formula to calculate the ISAL value. The formula will be given in the exams. Okay. So I think you may recall lah, seeing this formula from your economy class. Okay, so this is the growth factor, and this is the traffic categories. Okay, after you have calculated the ISAL design, you can categorize. You can categorize your ISAL here, whether and get the traffic category. In which category does your road lies? From T1 to T5. So this is the probability applied to the subgrade materials. But usually we just, this value will be given lah. Okay. Next, you need to estimate the properties of the subgrade. In our case, in our class, the CBR value, all of the properties for the subgrade will be given. Okay, I will not ask you to analyze geotechnics questions in the highway class. Okay, so when you have got the CBR value, you determine the SG, subgrade category. Oh, one thing I forgot to mention to you. There is a formula actually to use to estimate from the properties of the subgrade that has been given. From there, you can estimate the CBR value. That formula will also be given. Okay, so when you have got the CBR value, then you can get the subgrade category. This will also give you the elastic modulus, which is this is the range of elastic modulus, and this is the design input. What concerns us is the design input part here, because the elastic modulus is within this range. So if it is within this range, the design input is going to be here. So if this is within this range, the design input is going to be somewhere here. So you may note that the range here is overlapping, 50 to 100, and this one is 80 to 150. So 80 here also occurs here. Okay, we'll look into that afterwards. So properties of paving materials. Ini dah title lah kan. From the top of pavement downwards. This is referring to the figure that is being used by JKR. The topmost part, and then you have the road base, bituminous cone base, or unbound granular road base, or stabilized road base, and finally the sub base, unbound granular. So this is the material used for the design. So you can see for the drainage layer here, this is the code, the abbreviation, and this is the symbol. So primarily function granular layers with load distribution capability similar to subbase. And then you have this subbase cost. Okay, meaning that this is crushed granular material, or normally said as apa tu? Crusheran. Maximum is 10% fine. So it is GSB. Okay. Granular subbase. Crush aggregate. So this is for the road base, the CAB. So you can use for the road base here, you can use either a crush aggregate or wet mix or bituminous mix or STB. I forgot. What is this? Something stabilized lah kan? Stabilized. This stabilized with cement. Stabilized type 1 and stabilized type 2. STB1, STB2. Oh, saya tertutup ni. And this is the find the cost. Most common layer, which is AC28. It is being the designation is BC. And then you have the BSC here for the wearing cost. So for the wearing cost, you have not the typical one, AC10 or AC14 asphaltic concrete, or you can change it to polymer modified asphalt. Okay, so you can use the AC10 or AC14, but the bitumen that is being used is polymer modified. Or you can use SMA. Okay, there are two types of SMA, SMA14 or SMA20. Or you can use porous asphalt, either PA porous asphalt 10 or porous asphalt 14. And then you have this gap graded asphalt. Actually, SMA is already gap graded lah. Okay, GPA1 or GPA2, and stabilized base with bituminous emulsion. This is STD2 for wearing cost. But usually we use something, the top three here. The top three is the most common one. Porous is quite rare lah, but you still have it in some stretches in the highway. You can notice when it rains, there is no water, there is no film of water on the surface of the pavement. Okay, there is very little splash and sprays. So that is porous asphalt. It's very nice to uh, drive on when it rains, but the strength of the pavement is very difficult to achieve. Okay, so for wearing and binder cost, so the average temperature that is being used for wearing and binder cost for analysis is 35 degrees, and for road base is 25 degrees. This is for the testing part. Okay, in this manual, they are still using 8000 bitumen, whereas currently we have changed to 6070 bitumen. I'm not sure when they are going to change this, the elastic properties from 8000 to 6070. So this is the elastic properties of unmodified bituminous mixtures. The typical for AC10, for AC14, and this is for SMA, and this is for the van der Waals and road base. So you know the elastic modulus and the Poisson ratio. This is typical values. So if it is polymer modified binder, meaning that the mix is using polymer modified binder or bitumen, so these are the elastic modulus and the pavement ratio, Poisson ratio. So for the road base, it is treated similarly with bituminous binders and wearing costs. And the bottom of the bituminous road base is subject to fatigue load. This I already mentioned just now, kan? Alright. For crush aggregate and wet mix road base, the unbound granular materials used for road base consist of crushed rock and gravel with a grading that imparts on the mixture a mechanically stable course. Okay, ni teori dia je lah. That is capable of distributing effectively the traffic load. The performance of a well-graded granular is largely governed by their shear strength. So well-graded meaning that you have a good combination between fine aggregates, coarse aggregate, and fillers. So this is the key in designing a very good road base, because the friction between the materials, how the materials inside the mix interlocks with each other, will govern the shear strength and also the stiffness of the material. So the adequate shear strength and drainage is normally obtained when the fine material does not exceed 10%. Okay, so you can conduct actually research to have different combinations. So previous research has come to conclusion that if the fine material does not exceed 10%, you will get adequate shear strength and also drainage. Two types of granular base, crush aggregate and wet mix road base. Minimum CBR requirement for aggregate road base and wet mix road base is 80%, corresponding to the elastic modulus of around 350 MPa plus minus 100. Okay. Don't worry, the design procedure is very easy. Okay, stabilized road base. You normally use 3 to 5% cement or lime. Okay, where the strength here is modulus is 1800 MPa and the Poisson ratio is 0.4. So aggregate stabilized with combination of bituminous emulsion of foam bitumen and 2% of cementitious materials. The E value is 1200 and the Poisson ratio is 0.35. Okay, temperature, this one as already mentioned just now lah, mean annual temperature. This is air temperature, bukan pavement temperature. If you are being asked to about pavement temperature, it's not going to be 45. It's going to be in Malaysia around 60 plus. So this is the mean air temperature and also maximum air temperature. Okay, these are the effect of moisture to the performance of pavement. So this part actually we're going to cover tomorrow. Guys, 1 minute. I need to get this phone call. Okay, sorry guys. Kena angkat telefon sebab Prof ngor telefon. Tak boleh lah tak angkat kan. Deputy Dean. Okay. Okay. Apa tadi saya cakap? Terlupa dah. Measure. Okay. So the measures that you can take to reduce the to control lah the moisture induced damage is to prevent moisture entering the pavement system. This is the most important thing lah. Prevent moisture, of course, moisture cannot enter if your pavement is completely sealed, but that seal will crack. Whether it cracks 20 years or 15 years after the construction, or whether it cracks 6 months of the construction, then it is depending on how you design and depends on the loading that is being induced to the pavement. Sorry. Okay, so incorporate design features that remove moisture that enters the pavement system. This normally is geotextile lah. You have a layer of geotextile or drainage layer here that will actually protect, okay, from the moisture getting into the subgrade. And then you have the paving materials that are insensitive of the effect of moisture. Alright. Apa, ingat lagi tak? Do you still remember paving materials? The comparison, the most popular comparison is between granite and limestone. Granite is hydrophilic. It attracts water, it absorbs water. Limestone, hydrophobic. It repels water. In terms of strength, granite is better than limestone. But in terms of water, granite is a little bit, the performance is lower lah compared to limestone. So normally like in anything that we use, actually in life lah, you have to have a balance. Anything must have a balance. You cannot have too much of something, or it will become negative. The effect is going to be negative. Okay. Design period and reliability. Pavement design process cannot guarantee with certainty that the pavement will perform exactly. Okay, because compared to other fields in engineering, the pavement design is more or less apa tu, the accuracy is quite low. It's quite low actually, because to analyze the behavior of granular materials, to analyze the way that the subgrade handles loading is very difficult. So it is not really something that is as accurate as a structural formula, something like that. You can have something, formulas that is very accurate, but the variables that you put in probably came from an estimation method or estimation formula that is not accurate. So the accuracy of the accurate formula is actually not very good, because the parameters, the variables that you use is being estimated, unless everything is being you get the value is very accurate, accurate value of the variables, and then you get a very accurate formulas, then the answer is going to be very accurate. So in pavement field, this is sometimes can be a little bit unpredictable. So the traffic volume and axle loading spectra used as a design is approximation, and material properties used as design input are simplifications of complex variable conditions in a subgrade. And construction process do not usually produce a pavement in complete conformance with design specification. That is 100% correct. Even though you have everything, is the design is correct, the formula is good, it's no longer estimation. Everything is being calculated and designed accurately, and then the job was given to a contractor that doesn't care, and then continue the construction in a rainy day, and then everything is useless lah. That's the most of the case pun, selalu jadi macam tu. Okay. So due to the above mentioned reasons, the concept of reliability based on statistical parameters is adopted in the design. So reliability as an expression of the probability that a pavement constructed with reasonable conformance to the design and specs, and will support the design traffic for the design period without significant distress. Okay, so for example here, a probability of 85% applied to 10 years design of roads T1 and T2, and 20 years for road T3, T4, and T5. So the probability is just 85%. You are confident that this road is being designed appropriately, and it will not it will perform okay lah kan. It will have a good performance. Okay. So this is the design philosophy for the pavement structures. So you have in this manual lah, a minimum of 80 centimeters bituminous material for traffic category T3 or higher. Minimum 18 centimeters. Minimum combined thickness of granular road base and sub base is 30 centimeter. Combined sub base and road base. But the minimum thickness of the road base must be 20. So if you want to have a minimum thickness, 30 centimeter here, so your road base is going to be at least 20 centimeter, the sub base is 10 centimeter. Okay. This is for very low loading road lah, low volume. And this is the general conceptual outline. Okay. Relationship between the ISAL and the loading. Loading pula, pavement structure, sorry. Traffic category and T1, T2, T5. So you get here, if the ISAL is here, and the option that you can have is the combined thickness here. The thickness of bituminous layer is 18 centimeters, and the road base and sub base depends on the subgrade category here. If the subgrade, the CBR here is between 5 to 12, then the road base is 20, sub base is 20. Okay, if the subgrade here, the CBR is say 20.1 to 30, then the road base 20, sub base 15 centimeters. This is just the concept lah, conceptual outline. But for our design, we are going to use these figures. So you can see here we have several figures. The first figure here is for traffic category T1. Okay, where the ISAL is less than 1 million. Less than 1 million. Okay, so you have the option depending on the subgrade category here, and here is the pavement type. Okay, so you can use a conventional flexible granular base, where the layer here, on top here, the asphalt concrete, BSC, so this is the legend line, BSC is 50 millimeters. Okay, on top of, below it is CAB here, which is the crush aggregate, 200 millimeters. And you have a granular set base here, GSB, at 150 millimeters. If the subgrade category is SG3 or SG4 lah, here, you can see that the wearing cost here is still 50 millimeters. The crush aggregate base here is 100, and the GSB is can be less lah, 100 mm. Okay, so this is for T1 category. Okay, this is for T2, where the ISAL is between 1 to 2 million. Okay, you have three options lah: conventional flexible, deep strength, stabilized base, or full depth asphalt concrete base. Not concrete, asphalt concrete. Alright, so you can see here the BSC is 120, crush aggregate base is 200, GSB, granular sub base, is 100 millimeters. So it depends on the type of subgrade. And you have this for T3, and this diagram is for T4. For T4, where the traffic category, the ISAL is between 10 to 30 million, you can see that if the SG is 1, they don't recommend any layering. It says here that you need to upgrade, improve the subgrade. So meaning that you cannot use you cannot construct this pavement on top of a SG1 subgrade. Minimum is SG2 if the traffic is between 10 to 30 million. So this is for T5, more than 30 million ISAL. Same here, CBR 5 to 12 is not recommended. You need to improve the subgrade first, then only you can propose the layering thickness. The last one is the use for T5, a T5, but the use of polymer modified asphalt. Okay, so you have two options here: special purpose surface course or deep strength high modulus base course. Okay, so this is the for lower volume roads. So you have your ISAL here and subgrade. So you have the value of subgrade. Let's say the value is between 12 to 20, and the ISAL is 100 to 500. So you can directly use surface course of 50 millimeters, crush aggregate base 200 millimeters, and granular sub base 100 millimeters. You can choose from here. Okay. Example 1. Design a road pavement for 2-lane highway with average daily traffic 1350 vehicle, 16% are commercial vehicles. So in this question, you don't have the classification of the vehicles. You just you are given daily traffic 1350. From this 1350, 16% are commercial vehicles with unladen weight more than 1.5 tons. So solution, determine the design input. Okay. This is the problem with the current manual that we are using. Okay. The first question says that the the traffic is 1350. Suddenly in the solution, it says that a traffic count data indicate a 2700 vehicles in both directions. Of course, it's still 1350, okay, for one direction, but 24 hours period. But it does not mention in the statement of the question. So the actual question is here. So 2700 vehicles in both directions. So because it has two-way and 24-hour period, so you can just divide this 2700 to 2 into 1350. So if the design is based on data from HPU survey, the result is based on 16-hour survey, should be multiplied by 1.2. But for our case here, the counting is 24 hours period. So you can directly use 1350. Commercial vehicles 16%, no classifications. Lane distribution factor from the table 1.0, terrain factor rolling 1.1, design life 20 years, annual traffic growth 4%. This is from table 2.4 lah. You can get the value. So determine the design traffic. ADT, okay. So you use the ISAL year 1. This first formula lah. Okay, so where the percentage here is total percentage from the total value. Does not have any vehicle classifications. Okay. This is another mistake. It does not have LEF here. This is just 3.7. Two mistakes actually. This part is actually 3.7. When you calculate here, this is actually should be 3.7 lah in this formula. So you just multiply the ADT with the number of days per year, percentage of commercial vehicles. 3.7 is in the formula. It is not LEF. It is a factor 3.7, and then times L times T. You get 0.3 million. Next you calculate the design ISAL using the base year ISAL. So base year ISAL multiply with this TGF, where the growth factor just now it is mentioned at 4%. So refer to table 2.4, annual traffic growth, table 2.4, mana tadi? Okay, design period berapa tadi? Saya pun dah lupa lah. Ni lah kan. So for 4% growth, so the value is 29.78. 29.78. So you'll get the design traffic for 20 years at 9 million. So 9 million, okay, so 9 million is traffic category T3. Okay, between 2.1 to 10. So traffic category is T3. Actually, guys, I'm a close contact to somebody that get COVID last week. I haven't taken my PCR test yet. Take it later today. I was, I have a schedule to meet my students, my thesis students, 1 p.m. 2 p.m. today. So if any of you listening in this class right now, I think I won't be able to meet you today because I haven't test my COVID. I haven't taken the COVID test, and I just knew that I'm the close contact just before we start our class today.
Hope everything is okay, doctor.
I hope, yes, I hope everything is okay. But it has already been 1 week, and I think it should be okay, inshallah. So for my thesis students that I'm supposed to meet, thank you guys. That I'm supposed to meet today, 2 p.m. I think I won't be able to make it, although maybe I'll be going to UM just to log in or what. I don't know lah. I need to discuss with the head of department first lah, what I need to do. So whatever it is, I cannot meet you. So for your logbook, maybe I can sign it digitally lah. Even the technician has just gone out of quarantine. The highway technician has just completed his quarantine today, and he asked my signature for permission to work from home. But now I'm also probably I cannot go out. Ayo, problem betul. Alright, never mind. I'll sort it out with you guys later lah in our WhatsApp group. Okay. Sorry, I digress to the problem. So you have decided that this is traffic category T3. Alright. Next, we need to estimate the subgrade quality lah, subgrade SG category. So you will be given the CBR value, the standard deviation, and probability. So the CBR will be given here. Then you use this formula lah. 18% minus 1.282 multiply with 4.4. So actually this multiply with this, and then this minus this kan. Dia orang tulis kurungan, letaklah kurungan sikit kan. Ini semua boleh mendatangkan marah. Okay, so 18% minus 1.282 multiply with 4.4. Okay, so you get the percentage of CBR, 12.9%. Refer to this table. Okay, 12.9%, somewhere here. So it is SG2. SG2. Okay, SG2. Step 4, select from the figure. So you know that your the characteristic is T3 traffic, SG2 subgrade. So you can choose from the tables. Inilah. So this is T2. Tadi berapa tu? T3 ke T2? And SG2 kan? T3, SG2. Ini, somewhere here. So you choose from this table. So you have one of the option here. You can use the conventional flexible course, conventional flexible pavement granular base. So BSC 50, and then you have BC binder cost 130, crush aggregate base 200, and granular sub base 200. Okay. Example 2. Ini satu hal lagi. Pun ada mistake juga. Ni bukan mistake saya tau, ni mistake dalam manual tu, tapi saya terpaksa tulis. I just transfer the question from the manual to this slides. I cannot change it because it will confuse you. If you refer to these notes and then suddenly if I change it and you refer to the manual, it's different, you're going to get confused. So I just leave the mistakes here and then I'll inform you lah. Okay, average daily traffic 7286, 20% commercial vehicles, more than 1.5 tons. First one here. Soalan tak bagi tahu pun dia ada different classification. Suddenly in the solution they gave us these values. Volume. Okay. First of all, I must these values need to divide by 4 lah. Because you have 4 lane freeway. 7286 divide by 4. But if the distribution of vehicle classes are given like this, you need to know that, need to make sure that the total of this, and this should be equal to this value divided by 4. Okay? Whatever it is, if you are given one lump sum value, then the formula is going to be the first formula. But if you are given like this, where they have split into commercial vehicles, vehicle class 1, 2, 3, and 4, then you need to split it. Okay, since, although it is not mentioned in the question, since the data here is taken from HPU survey from 6 a.m. to 10 p.m., you need to multiply with 1.2. Okay, so you get the actual vehicles, number of vehicles per 24-hour periods. So for vehicle class 1, class 2, class 3, and class 4. And then you have the lane distribution factor from the table, and then terrain factor, and design life, and growth. So use this formula because you have different category of traffic. So ADT CV1 multiplied with LEF1. So CV1, apa tadi, small lorries. Beritahu tak sini? CV1 749. CV1 for 749. CV1, which is small lorries here. So the LEF is 1.0, 0.1. Okay. So this is, so you continue lah with CV2, CV3, CV4. Okay. Multiply with 365, lane distribution factor, and terrain factor. You get the ISAL for year 1, 1.363 million ISAL. And then you project the ISAL to 20 years towards the end of the design period. So R is the growth and N is the number of years. You can use this formula lah. Okay, so you calculate, you get 42.7 million, and it can be concluded that the traffic category is T5. And then you are given this falling weight deflectometer value for the subgrade. So this is not CBR, this is falling weight deflectometer test. 165 MPa. The standard deviation for the test is 28 MPa. Reliability is at 95%, 1.645. So you use this formula, again, ni dia ada kurungan pula. 165 minus 1.645 multiplied with the standard deviation. So you get the subgrade characteristic subgrade modulus is 119 MPa. Okay, 119 MPa, you should not jump to conclusion to subgrade category. You need to take this value and plus with 165, which is the mean of the FWD results here, and divide by 2. This plus this divide by 2, you will get more or less 140 MPa. Using this 140 MPa, then you can get this and conclude that it is SG3. It can be SG2 here because the range for SG2 is also between 80 to 140. But the design input for SG2 is 120. Okay, this is imperfect lah. To me, this method need to be improved. Okay, so since the value that we got is 140, your SG is SG3. All right, so mana tadi? T5 SG3. First option here. T5 SG3. You can use either this, or this. First three options. Or you can use polymer modified asphalt 35 SG3. You can use this and this, or this. Okay, this one is very thin, but this is polymer modified base, 220 thickness. This is very expensive because the base is being modified with bitumen, polymer modified bitumen. Once you get into the rearms of polymer modified bitumen, then the cost is very high. Okay. All right. So you can choose lah, either one, either mana-mana. Option 1, option 2, and the polymer modified here. It is not mentioned in this example. So last example, example 3. A design road pavement for 2-lane rural road in a hilly setting. Assume a design period of 10 years. The volume of commercial traffic is less than 100 CV with unladen weight more than 1.5 tons. The traffic volume over the design period is 100 to 500,000 CV. So refer to table 4.1. So the calculation here, the ISAL is between 100 to 500,000 ISAL lah. CBR is given, it's not given in the question, but it's given in this tab here, 5 to 12. So only with these two pieces of information, you refer to this table, table 4.1. So CBR value, and this is the ISAL value, and this is the thickness of the different layers here. Okay. So this is, you have two options. Either you use table 4.1 or you can use figure 3.1 where it is T1 and SG1. This one. T1, SG1. So you can choose either this or table 4.1. This is for low volume roads. Okay. Any questions or not? Please study today's examples. It's very important. Okay, guys. If there is no questions, I'll end the class here. We'll have our last class tomorrow, 5 p.m. Where we will discuss the exams as well. Thank you very much, everybody. Have a nice day.
Doctor,
Yes.
sorry, can I ask something regarding the assignment 2?
Yep.
Because yesterday I texted doctor about the negative